Hello everyone. In this video, we will see if a person is affected with Parkinson's syndrome with the help of machine learning. So in this project, we will predict if a person is suffering from Parkinson's disease or not based on his audio or voice measures. So over here, we have done our imports, and in the first line, we can see that I've imported pandas. So what pandas really does is that it will help us to create data structures and manipulate these data structures. So we are going to read our data using pandas, and we will also edit the data frame with the help of this import, which is called as pandas. Over here, as you can see, after pandas, we have imported NumPy. So NumPy actually stands for numeric Python, and NumPy is a Python library which will help us to work with arrays. And at the same time, NumPy also deals with matrices and algebra. And over here, we have imported Seaborn. And what Seaborn does is that Seaborn is actually a data visualization library. And this Seaborn, it is based on matplotlib. What it really does, that it will help us to visualize statistical graphs of our data. And then over here, we have matplotlib.pyplot. So matplotlib, it is actually a plotting library, and it will help us to plot our data. And then over here, you can see I've imported train test split. So what train test split does is that it will help us to divide our data into training and testing parts. And after we train test split, we are currently using three machine learning models over here. One is the logistic regression, and then we have our random forest classifier, and later we have also used other models like the decision tree. We'll find out all the results of these models, and in order to evaluate these models, we will need the help of evaluation metrics. And over here, these are the evaluation metrics which I have imported, and we are going to evaluate our model with the help of accuracy score and confusion matrix. So let us go ahead and look at our data. So over here, I have read the data set. The data set is called as the Parkinsons.data, and it is a CSV file. And that's the reason why we have used the pd.read underscore CSV function over here. And after we have read our data, we'll load the data. And as you can see, this is our data frame. I have actually loaded the data in DF, and this is our DF over here. This is our data set. And in this data set, as you can see over here, we have a status column. This status column is nothing but our target column, and it is this column that we are going to predict with the help of machine learning. And over here, as you can see, these columns are nothing but they are the audios of a person, and they are the audio recordings, and these are the attributes of those recordings. We have MDVP hertz and MDVP FHI hertz and so on. So I have attached a text file. Please check the text file over here. This text file over here shows us the individual columns, what they actually mean. And this gives us a description of the data. And as you can see over here, attribute information over here shows us that MDVP FO hertz is the average vocal fundamental frequency, and MDVP FHI hertz is the maximum vocal fundamental frequency. And this description file also mentions the source of data collection. And let us go back to our data frame over here. So for data understanding, I have used df.shape. So what this line really does is that it will display the total number of rows and columns present in our data set. So as you can see over here, using df.shape, we see that there are 195 rows and 24 columns, and this displayed the total number of rows, as you can see. And then over here, the other data understanding part is we have to check if there are any null values present in our data set. and that can be done using the df.isnul.sum. So what this code really does is that it will display us or if there are any null values present in our dataset. So when it comes to name, you see a 0 over here. That means that there are no null values in this particular column. And so as you can see over here, every value over here is 0. That means that there are no null values in our dataset for now. And over here, the other understanding that we can do from this data is we can use df.info. What df.info shows us is that it displays us two things. Over here, as you can see, these are our column names, and we have a name column, and over here you can see that there's object mentioned over here. So df.info shows us what kind of a data is present in our data set. So in this column name, you can see that we have object mentioned in it. So it means that the data is categorical in nature. Let us go ahead and check this column. And as you can see over here, we have strings in our column name. And that's the reason why we have object mentioned in the df.info over here. And looking at another column, we have mdvp fo hertz, and you can see over here that it is a float type. So float is mentioned when our data is in decimal part. Whenever we have decimal data, then we get a float when we use df.info. So it is this column which has float in it. So almost every column is of float type. And the other columns over here, like the status, as you can see over here, it is mentioned in integer type. So let us go ahead and check this column status. And as you can see over here, there are only two types of numbers over here, which is 1 and 0. And this is not of any decimal value. And that's the reason why we see an integer type using the df.info on that particular column. And the other thing that df.info shows us is that it shows us if there are any null values present in our data. As you can see over here, df.info shows that there are total 195 columns in our data set. And among them, we see that there are 195 non-null objects in it. That means that there are no null values in that particular column. When we have a mismatch in these two numbers, let's say we had 195 rows and over here we only had 100 rows, then it would mention that jitter column had some null values present in it. So over here, but as we can see that there are no null values in it, so we can move ahead. And then I've used df.describe on this dataset. And what this function really does, it is actually used to calculate any statistical data like percentile, mean, and standard deviation of the numerical values of the series of data frame. So this works only for numerical type data. If we had any categorical data, then we would not get any values over here. Like we had a column called as name, and then we had a column called as mdvp. And over here you can see that we do not have any column called as name over here because it is of categorical type. And over here you can see that we have these 8 rows and 23 columns. So the describe function shows us all the statistical values like standard deviation and mean. Over here, other thing that we can see in this describe function is that it shows us the minimum and maximum values present in a particular column. Over here, we can see that in this mdvp column, the minimum value present in this column is 88, and the highest value that is present in this column is 260. And similarly, you can see the same thing repeats for other columns as well. Over here in mdvp fhi hz or hertz, we can see that the minimum value over here is 102, and the maximum value present in this particular column is 592. And let us see for the status column. Alright, we already know that there are only two values present in our status column, that is 0 and 1. Each value in the status column is represented if a particular person is affected with the Parkinson's syndrome or not. And over here we have used another function called as df.columns. So the df.columns will show us all the column names present in the data. So as you can see here, we have columns like the name, MDVP, FOH. So the column names that you cannot see over here is represented with three dots. So we cannot see the column names in between. So in order to check the other column names as well, we can use something called as df.columns. And over here, uh, this is the attribute information. So it's best to refer to this file over here because medical terms have been represented here. And let us read a few lines from this text file. So this data is composed of a range of biomedical voice measurements from 31 people. And among these 31 people, 23 of them were suffering from the Parkinson's disease. And each column in the table is a particular voice measurement. So whatever we see over here in the data is nothing but voice measurements taken by people, among which 21 were really affected with the Parkinson syndrome. It's not 21, it's 23. And the total number of people were 31. And over here in the attribute information, as we saw earlier, this refers to average vocal fundamental frequency, maximum vocal fundamental frequency, minimum vocal fundamental frequency, and so on. More research must be done on these values in order to further improve our model, and feature engineering can be done to understand each feature and improve the model's performance ahead. And so over here we have printed our status column, which is our target column over here. And you must wonder what these 1 and zeros are. So 1 over here refers to Parkinson. I mean, if we see a 1, it means that the particular person is affected with the Parkinson syndrome. And whereas where zeros are mentioned over here, 0 means a person is not affected with Parkinson syndrome and is in a healthy condition. So let us go ahead and do some visualization on this data. So over here, we have our plot, and we can see that most of the people in the data set are affected with Parkinson's disease. As we saw earlier, that one refers to Parkinson syndrome, and we have less people who are healthy in that particular data set. And this is the second visualization. So the second visualization over here shows the status on the x-axis, and we have the NHR value over here. So the patients affected with Parkinson's disease have high NHR value for that particular person, and which is nothing but NHR is the measure of ratio of noise to total components in the voice. So NHR value is high in the people who are affected with Parkinson's syndrome, and the NHR value is low for the people who are not infected or affected with the Parkinson's syndrome. It is basically a syndrome, not an infection. So the NHR value is low for the people who are not affected with the Parkinson's syndrome. And over here, we have taken status on the x-axis and HNR value on the y-axis. So this visualization over here shows us that the HNR value is high in the people who are healthy, and the HNR value is low in the people who are affected with the Parkinson's syndrome. So let us read this comment over here. The patients affected with Parkinson's disease have high HNR value. That is the measure of ratio of noise to total components in the voice. Let's move ahead with the other visualization over here. And over here, we have taken a status on the x-axis, and we have taken RPDE on the y-axis. So RPDE over here, it's nothing but non-linear dynamical complexity measure, and RPDE is high in the patients affected with Parkinson disease. So as you can see clearly that this value is high in the people who are affected with the Parkinson syndrome. And Over here, the other visualization that we have done is that we have created a distribution plot. So a distribution plot, it is basically used to check if our data has skewness in it or not. So as you can see over here, I have used 3 rows and 7 columns, and this is how our distribution plot looks like. Over here, you can see that we have given a figure size of 16,4, and we have taken the column names from the data frame. The other thing that can be noticed over here is that I've given an index value equal to 1. So what this really does is that it will avoid the first column and start visualizing from the second column. As we can see that distribution plot only works for numerical values, and over here our first column was the column called name, and this name column is of object type, and that's the reason why we have given an index value as 1 in order to avoid that column. And the visualization over here starts from the second column, and this is the MDVP FO hertz again. And over here you can see that the distribution plot shows us that there is no skewness here. And the other thing that the distribution plot shows us is that it displays a distribution and range of set of numerical values which are plotted against a dimension. And for now, we don't need to use any log transformation. And let us go ahead, and over here you can see that we have dropped the name column, and name column is actually of no use for our model, and that's the reason why we have dropped the column name. And then the other thing that we have done is we have separated our data into independent and dependent variables. And as you know that our column called as status is our value that has to be predicted, and that's the reason why we have taken status on y, which is nothing but our target variable. And as you can see over here, this is the x dot head, which has all the columns from MDVP FO hertz, and other such values are present in our x dot head, but we do not have the target column in this part of data, and we have given that target column to y. And as you can see, this is the y, and the y has target variables in it, which is nothing but 1 and 0. And over here, after we have split our data into independent and dependent variables, the next thing that we have done is we have train test split our data. So what this really does is that you must remember we have imported train test split. So this is the code related to the import called as train test split. So this piece of code, what it really does is that it will convert data. It will basically divide the entire data frame into training and testing part. So over here, we remember we had this x dot head and y dot head, which had the independent and dependent columns in it. So the train test split will divide data into training and testing part, and the test size over here mentions that around 20% of the data is going to get used for testing purpose, and the remaining 80% of the data will be used for training purpose. And over here, if we change the value from 0.2 to 0.3, then the training data will have 70% of the data, and testing size being 0.3, 30% of the data will be used for test purpose. And the next thing that you can see over here is that we have used a random state over here. Here the random state is mentioned as 40. So what random state does is that, let's say 2 people among 5 people use the same random state, then the 2 people are going to get likely results which are going to be similar, and having the same random state will give those people the same results. And over here we have printed our x train shape, x test shape, y train shape, and y test shape, and these are the shapes over here. Uh, the next thing that we have done is we have used machine learning, and as we remember, the previous imports above had logistic regression and random forest classifier, and this is the logistic regression. And the logistic regression model has been used over here, and the model has been fit on X train and Y train. And over here we have predicted the same model on X train, and over here we have the print command. So print command will print the accuracy on X train, and the next line over here, we have used model.predict on X test, and this print command over here will predict the model accuracy on testing data. And as you can see over here, we have given this line of code. What this print command will do is that it will create a dotted line, which will repeat for 50 times. As you can see over here, we have this dotted line, and then we have used a confusion matrix. And confusion matrix is another evaluation metric that we can use to find out how well our machine learning model is performing. And a confusion matrix will tell us like how many predictions were classified correctly or incorrectly. So this way we can compare the confusion matrix with other models confusion matrix and come to a conclusion like which model performs better compared to other. And over here you can see that our model accuracy on train is 87, and the model accuracy on test is 84, and this is not a bad model, and the accuracy is good. Let us see how the confusion matrix performs. And over here we have our confusion matrix, and for now the logistic regression has given us an accuracy of 84%. Let us see how the other models perform, and we'll also compare how the confusion matrix has performed on the other models as well. And over here we have random forest. So random forest is a type of machine learning. It's actually a robust machine learning algorithm that can be used for a variety of tasks. Like we can use this machine learning model for both linear regression as well as classification problems. So this works well on regression and classification use cases. And what a random forest really does uh, is that it is actually made up of a small number of decision trees. Like it is a collection of many small decision trees, and a random forest is also again called as an ensemble method. So let us see how this model works. And over here we have fitted the model on X train and Y train, and again we have predicted the model on X train, and this line over here will print the model accuracy of random forest on the X train, and then we have predicted the random forest model on the X test, and this line over here will predict the model accuracy on test. And over here we have used a confusion matrix, and the confusion matrix over here, as we talked before, will show us how many predictions were correctly made and how many predictions were wrongly classified. And as you can see over here, our model accuracy on training is 100, and the model accuracy on test is 89. And over here we have 897. And as you can see, our logistic regression had 84%, which shows us that random forest worked well as compared to logistic regression. And let us see the confusion matrix. We can use this confusion matrix to predict the total number of wrong predictions made. And as you can see over here, 4 wrong predictions were made out of 39. And we might need more data for this model, as we have only 39 predictions in total. And as you can see, only 4 predictions made were wrong out of the 39. And then we have used a kappa score, and kappa score is another way in which we can use this kappa score to evaluate how well our model is performing. So what a kappa score really shows us is that Kappa score or Cohen's kappa coefficient is nothing but a statistic that is used to measure inter-rater reliability and also intra-rater reliability for qualitative or categorical items. So as you can see over here, our kappa score value is 68, and let us compare it with other models also. For now, what we have done, we have predicted the results and we have created two columns over here. One is the predictions and the original values. And as you can see over here, we have saved it to a data frame, and the 0 and 1 are nothing but our predicted and actual values. And this data frame, you can see that the 0 column is nothing but our predicted value. So this column holds all the predicted values, and this one is nothing but our true value. So as you can see over here, there are a few wrong predictions made by our model, which were nothing but 4 by 39 as we saw earlier. And this is our prediction as well as actual values. And random forest has performed very well compared to the logistic regression. And let us see how other machine learning models perform. And for that, we have done some imports over here. We have imported a Navy base, and we have imported decision tree classifier, and then we have also we have already used the random forest classifier. So the next import is our k nearest neighbors. So let us go ahead with our decision tree classifier. And as we know, what a decision tree does is that it builds regression and classification models in a form of tree, and decision trees can hence be used for both use cases, including regression, where we have a decision tree regressor, as well as for classification, we can use the decision tree classifier. It works well on both. And what it really does is a decision tree will build a tree structure. It will actually break down a dataset into smaller and smaller subset, while at the same time an association tree is incrementally developed. So it usually breaks down a dataset and create a decision tree out of it. And over here we have done our fit. We have done the model.fit or the decision tree classifier.fit on X and Y. And then this is the model.predict. We have predicted the decision tree on X train. And as you can see over here, we have printed this model accuracy on our X train. And then next thing that we have done over here is that we have predicted the model on X test. And this is the print statement for that for the model accuracy on X test. And as you can see over here, that we have a model accuracy on train as 100, and the model accuracy on test is 100 again. So this is a clear case of an overfit, and the decision tree has overfit on our model, as we have high accuracy on train and test, and we have 100% accuracy, and that's not a good model. So let us see how the confusion matrix performs. And as you can see over here, as we have higher accuracy on train and test, our model says that there are no wrong predictions compared to other models, and this model cannot be used, and other models should be tried. And this is a clear case of overfit, and as you can see, we are having a kappa score again, which is 100%. So let us move ahead and use another model. So as you can see over here, we have used a Navy based classifier. And what a Navy based classifier means is that it is actually a collection of classification algorithms, which is based on Bayes' theorem. And it's not actually a single algorithm, but a family of algorithms. And so let us see how the Navy based classifier has performed. And as you can see, we have used the Navy base, and we have done the Navy base fit on X train and Y train. And over here, we have fit the model, and we have printed the model's accuracy on X train. As you can see, we have fitted the model on X train first, and then we fit the model on X-test, and then simultaneously we have printed their accuracy on train and test as well. And over here you can see that the model accuracy on train is 73% and the model accuracy on test is 69. And so far the random forest model has performed very well, and no other model has performed as well as the random forest classifier so far. And let us see how the confusion matrix looks like. And we have used our confusion matrix, and as you can see over here, the total number of wrong predictions made is 12 out of 39, which is again not a good model, because we had a random forest model which had given us 4 wrong predictions out of 39, as you can see over here. So let us go ahead and use another model except for navy base. And over here, we have used k nearest neighbors. So k nearest neighbors, or KNN, is a algorithm which is called as the simplest classification algorithm in machine learning. And KNN is non-parametric. The KNN is also called as lazy learning algorithm. Let us see how the k-nearest neighbors model has performed. And the same thing has been repeated as before. We have fit the KNN model on X train and Y train, and then we have predicted the KNN model on X train, and then we have printed the k-nearest neighbors accuracy on train, and we have predicted the accuracy on test. And as you can see over here, our model accuracy on train is 91% and the model accuracy on test is 84. I think this is an improvement as compared to the logistic regression. Uh, I mean the random forest regression. As you can see, the random forest classifier and the k-nearest neighbors has given us 89% accuracy on test, but the total number of wrong predictions on k-nearest neighbors is 6. Again, we can say that the model accuracy on test is as similar as the random forest classifier, but the model is not as better compared to the random forest classifier, as we have 6 wrong predictions by 39. And currently, the random forest classifier is on top. And over here, we have used the kappa score. The kappa score is 48, and the kappa score is not as high as the random forest classifier. So let us go ahead and use another model, and this is the last model that we have used, which is the support vector machine. So support vector machines, or SVM, is called as a supervised machine learning algorithm, which can again be used for both classification and regression challenges. However, it is mostly used in classification problems. And in this algorithm, we plot each data item as a point in n-dimensional space. So let us see how the support vector machine has performed. We have used a kernel over here, and the kernel is called as linear kernel. And then we have fitted the SVM model on X train and Y train again. And then this is the support vector machine model predict on X train. And this line will again print the model accuracy on train. And then we have the SVM model predict on X test, and this line will print the model accuracy on test. And as you can see over here, the model accuracy on train is 87 and the model accuracy on test is 89. This is again similar to random forest classifier as well as the k-nearest neighbors. No, it's not similar to k-nearest neighbors. It is actually similar to the random forest classifier. And we have used the confusion matrix over here. And using the confusion matrix, we can clearly see that the total number of wrong predictions are 4 by 39. And this is again totally similar to the random forest classifier. So we can say that the random forest classifier and the support vector machines have given us a similar accuracy. and the total number of wrong predictions made by these two models is again similar. Let us compare these two models and see which model performed well. Let us go ahead with, we'll just see how the kappa score varies in both the models. So here in the support vector machine, our kappa score is 65. Let us see how the random forest model has given our kappa score. And as you can see, the kappa score over here is 68. So far, the random forest classifier and the support vector machines have performed very well and gave us an accuracy of around 89 percent, and the total number of wrong predictions they both gave us were 4 by 39, and the model can be further improved. The machine learning part can be improved by adding more data. Currently, we just had 190 rows, I mean 195 rows. More data can be used, and we can check the overall performance of all the machine learning models. And so far, what we really did was that we imported the necessary libraries, and then we read the dataset uh, using the pd.read function, and then we did some data understanding by using the df.shape, finding out the total number of rows and columns, and then we checked if there were any null values present in our dataset. And using the info function, we saw if there were again any null values present in our dataset, and we also checked the types of the data present in these columns, whether if it was object type or the integer type or float type. And then we use the df.describe function and saw the statistical data of this dataset. We found the percentile, mean, and standard deviation. We also checked the minimum and maximum values present in these columns. And then in order to display all the column names, we use a function called as df.columns and saw the total number of columns present in it and what these columns were called. And these columns are medical terms, and I would really suggest you to go through the text file, as the text file has the description of these particular columns. And after that, we saw the target column, and we saw the values present in the target column, which were given to us as 1 and 0, where 1 showed us that the person was affected with the Parkinson's syndrome, and 0 implied that he was a healthy person. And then we did some visualization and checked these medical values as well. So wherever we had one as infected or affected with the particular disease, we had a higher NHR value. And if a person was healthy, then his HNR value was high. And such visualizations were seen. And then we used the distribution plot, and distribution plot showed us that there was if there was any skewness in the data. And whenever we find that the data is not distributed normally, we could go ahead with using log transformation, but that was not needed in our case. And then we split our data into dependent and independent variables, and then we used a train test split to divide our data into training and testing part. We used the 80% of data for training purpose, and we gave the 20% data for testing purpose. And then we saw what the random state was all about. And then we use machine learning. We use models like logistic regression, random forest, uh, and then we used the decision tree, and we use the support vector machine, and we also use the navy Bayes classifier. And at the same time, we have also used KNN model. And among all these models, we saw that the random forest classifier and the support vector machines perform very well. The model's overall performance can also be increased with the help of hyperparameter tuning. Like each and every model can be further hyperparameter tuned in order to find the correct hyperparameters, and those hyperparameters can be assigned to these machine learning models, and we can check the accuracy of these hyperparameter tuned models, and that will increase the accuracy of our models again. And but for now, we will use the random forest classifier in order to continue with our machine learning project. And so we have like successfully used our machine learning models in order to predict if a person is going to get affected with Parkinson's syndrome or not. And that's it for this video. Hope you like this video, and until then, have a good day, and I'll see you soon in the next video. Take care.